For this film, you will need a notebook and pencil, and you must be ready to take readings from the screen. Using this apparatus, we're going to measure big G, the Newtonian constant of gravitation. Mounted firmly on a vibration-free wall is this torsion balance. There are two lead spheres. They're each of mass 15 grams, and they're suspended in a special chamber from a thin bronze wire. There's a small mirror fixed to the balance. 5 meters away, there's a scale. This is graduated in centimeters and millimeters, and you'll shortly be taking a lot of readings off this scale. If we switch off the laboratory lights and turn on the lamp, there's the mirror reflecting the light, and there's the image which it throws on the scale. We must first find the period of oscillation of the torsion balance so that we can calculate the torsion modulus of the bronze wire. To do this, we set the balance swinging using a magnet. The movement isn't very great, but it's magnified by the use of the beam of reflected light which acts as an optical lever. After a while, the oscillations damp down and we can measure their frequency as the band of light moves more slowly to and fro across the scale. We'll use this clock to time the oscillations. Get ready to take down a lot of readings. We're going to observe the position of the band of light on the scale as filmed every 2 minutes over a period of nearly half an hour. You must note down the position of the middle of the band to the nearest millimetre or so at 2-minute intervals. We're coming up to the first reading now, which will be at 1 minute. Make a note, 1 minute, and we'll count you down from 5 seconds to the minute when you must judge the scale reading and write it down. 5, 4, 3, 2, 1, now. We made that 1 centimetre, 1 centimetre. We'll give you a short pause each time. Now coming up to 3 minutes. Write it down, 3 minutes. 5, 4, 3, 2, 1, now. We made that 27.5 centimetres. Write down your estimate. Now coming up to 5 minutes. Note it, 5 minutes. 5, 4, 3, 2, 1, now. Now for 7 minutes. 7 minutes. We'll count you down again. 5, 4, 3, 2, 1, now. Next, 9 minutes. 9 minutes. 5, 4, 3, 2, 1, now. "11 minutes. 5, 4, 3, 2, 1, now. We made that 7.6 centimetres, but write down your reading. Now for 13 minutes. 13 minutes. 5, 4, 3, 2, 1, now. "15 minutes. 5, 4, 3, 2, 1, now. 17 minutes, 17 minutes. 5, 4, 3, 2, 1, now. "19 minutes. 5, 4, 3, 2, 1, now. We made that 27.6 centimetres, but you put down your estimate. Now 21 minutes. 5, 4, 3, 2, 1, now. "23 minutes. 5, 4, 3, 2, 1, now. "25 minutes. Only one more after this. 25 minutes coming up. 5, 4, 3, 2, 1, now. "27 minutes, 27 minutes, the last reading. 5, 4, 3, 2, 1, now. From those readings, you can later on make a graph which will give you the period of oscillation of the torsion balance. Now, for the next part of the experiment, we shall measure the deflection of the torsion balance by accurately known masses mounted close to its two lead spheres. To begin with, we'll use two flasks containing mercury, each of mass 1.01 kilograms. We first swivel them to this position. They exert a gravitational pull on the lead spheres of the torsion balance, causing a deflection. This operation disturbs the delicate balance, and we can't take a reading until it settles down. This takes a few hours. Now write down this scale reading. Again, judge the position of the center of the band of light to the nearest millimeter, and note that this is for masses of 1.01 kilograms. We now swivel the two flasks to this position so that they exert a gravitational pull which twists the suspension in the other direction. Again, we wait for several hours for the balance to come to equilibrium. Now write down this scale reading to the nearest millimeter for the flasks of mercury in the second position. Now we take off the flasks, and we're going to measure the deflection caused by two objects of greater mass. They're two lead spheres, each of mass 1.50 kilograms, and they're supported in the same positions relative to the lead spheres of the torsion balance as the flasks of mercury were. First we swing them to this side, and after an hour or so, take the scale reading. Write this down for the 1.50 kilogram masses in the first position. Now to the second position. And write down this scale reading. Finally, we'll use greater masses still, which will cause an even bigger deflection. These are lead spheres, each of mass 2.96 kilograms. They're at the back there. And the supports have yet again to be adjusted so that we can place them in exactly the same positions relative to the small spheres of the torsion balance. To the first position, leave it to settle down, and note this scale reading for the 2.96 kilogram spheres in the first position. To the second position, then wait for equilibrium. And write down this last reading. You must now use the notes which accompany this film. They explain how to make the calculation and give you the dimensions of the torsion balance which you need, the dimensions of the flasks of mercury and of the 2 pairs of lead spheres, and the distance from the mirror to the scale. From this data and the readings which you have taken during the film, you can work out a value for the constant of gravitation.